remind everyone to remain muted for the whole duration of the presentation, and only unmute yourself during the question time. And a reminder that we are going to record the presentation until the question times, and later I think for the questions, as usual, you just raise your hand, or you put a Q or a question in the chat, but do this only at the end of the presentation. Okay. So I don't know, Annalise, if you want to start. Again, welcome everyone to this second Kavli lecture, and you are very glad to have Ravit Helled. She graduated in Tel Aviv, and then she was postdoc at US and assistant researcher at UCLA. And then she moved back to Tel Aviv, where she was assistant professor and associate professor. And now she is associate professor at the Institute of Computational Science at the University of Zurich. And she is a well-known expert in the area of planet formation, of planetary interiors, especially for what concerns giant gaseous planet, and both in our solar system and in the area of exoplanets. And she, within this context, she is co-investigator of the JUICE mission, the ESA mission. She's also part of the Juno mission, as you see from her first slide, Plato, and also she's part of the Ariel mission, which you may know has been approved by ESA, I think, last week or 4 weeks ago. And I think she will give an overview of her field and of her recent results. Thank you, Ravit. When you're ready, you can start.
Yes, thank you very much. And I'm really happy to be here. But I have to say that I would have been even happier to be there in person, because I think Cambridge is great and I have colleagues and friends there, but I hope that's next time. Okay, so today I'm going to tell you about giant planets and where we stand in the field. Okay, so my talk outline is the following. I will give a short overview. I will talk a little bit about giant planet formation, planetary interiors, then how we can use Juno mission results to better understand those aspects, and I will end up with conclusions and future perspective. So the big questions in the field, how do planets form? We want to understand how these very common astrophysical objects are forming. What is the occurrence rate of planets? What are the compositions of exoplanets? Are there habitable worlds? At the same time, we want to understand what are the compositions of the planets in our own planetary system, and to understand the uniqueness of the solar system. So these are really the guiding questions of the field. And today I'm going to talk about giant planets. So giant planets are not habitable, maybe their moons are, but they are very important for our understanding of planetary systems. And this is because of two main reasons. The first is that they shape the architectures of planetary systems. This is because they are very massive and they form early. And because of this early formation, they can really excite small objects. They change the dynamics of the planetary systems, and they can also lead to delivery of volatile materials, like we think is the case for our own planetary system, with Jupiter providing icy objects to the Earth. And that's why about 30% of the water is actually due to comets that were excited by Jupiter. And the second reason is the composition. Because they are hydrogen and helium dominated, they can provide information on the physical and chemical properties of protoplanetary disks where planets form. And therefore, it is really important to constrain the composition of giant planets. So here you can see the giant planets in the solar system, and you can clearly see that these are the dominating planets. It doesn't mean that if you're bigger, it's better, but it is clear that in terms of mass, in terms of dynamics, these are clearly the dominating objects. So in our solar system, we have 4 giant planets, but now we also know that there are giant planets around the stars, and these two groups are somewhat different. So before we discovered exoplanets, our knowledge was linked just to the solar system, and we could infer the following conclusions: that giant planets exist at large radial distances, so larger than 5 astronomical units, that the mass is decreasing with radial distance, so Jupiter is more massive than Saturn, which is more massive than Uranus and Neptune, and that the metal enrichment is increasing with decreasing mass, which means that Uranus and Neptune are more metal rich in comparison to Saturn, which is more metal rich in comparison to Jupiter. But then we had giant exoplanets, and suddenly we were surprised. So we have many more objects, but on the other hand, we have information only on their very basic properties. So we know that they exist, but we also know that they are less common than smaller planets. The occurrence rate is between 5 and 20%, depending on the stellar mass and metallicity. So again, they exist, but they are not as common as small planets in the galaxy. We also know that giant planets exist at very small radial distances, but also at very large radial distances, which is not the case in the solar system. And we know that giant planets come at various masses and metallicities. So what we try to do is to combine these two complementary groups, where here for the solar system, we have only 4 objects, but we have accurate measurements in comparison to giant exoplanets, where we have the statistics, but again, we have the mass and the radius, and if we are lucky, also the atmospheric compositions, and try to link these two aspects to better understand giant planets as a class of astronomical objects. And when we think about characterizing giant planets, it always comes back to Jupiter, because really Jupiter is used as a giant planet prototype. Nevertheless, we have key fundamental questions that are still open regarding Jupiter. So the formation of Jupiter, how did it form? Where did it form? How long does it take for a giant planet to form? How many heavy elements do we have in Jupiter? How much water? Does it have a core? And if it does, how massive it is? So again, these are fundamental questions that we try to answer regarding Jupiter, but of course, this also is reflected to our understanding of giant exoplanets. And here you can just see some of the basic parameters that we know about Jupiter. So you have the mass, it's more than 300 times the mass of the Earth, 318. It is located at 5.2 astronomical units. Of course, it's a large object. And again, the composition, we know it's hydrogen helium dominated, but we don't know what is the exact mass of heavy elements. Also, it's a fast rotator. Of course, this is you can see just by looking at images of the atmospheres of Jupiter, but I'm not going to talk about it today. Here, I'm going to show you a plot that shows the core mass estimate from theoretical models as a function of the year of study. I really like to show this, this slide. So what do we see here? First of all, the y-axis, again, this is the inferred core mass. It's in Earth masses. You can see, okay, it goes up to 40. And this is the year of study. So it started at the late 70s and it's still continuing today. So what do we see? We see that at early times, the estimated core mass was rather high. So it was 40 and then between 20 and 30. And this was linked to the existing equation of state of hydrogen that was available at that time. So the core was estimated to be relatively massive. Nevertheless, given the total mass of Jupiter, which is 318, you can see that it's not a very large fraction of the total mass, but it is not negligible. Then there was a convergence a little bit towards smaller masses. At the late 90s and beginning of the 2000s, it was also popular to have zero core mass. That's when the disk instability model somehow was revived. But you can see that in a way there is no convergence, right? So then later on in the 2010s or later, suddenly there were also solutions with higher masses. So what are the conclusions we can take from this figure? First of all, people try to infer the core mass of Jupiter since decades. This is really an important goal in planetary science. And then the second thing that you can see is that we are not converging. So we still don't have this very accurate estimate for this property. And nevertheless, people keep trying to constrain this property. And the reason that this is very important to put limits on the core mass of Jupiter is because it is linked to giant planet formation. So a little bit about giant planet formation. There are two models. for giant planet formation. There is the standard one, core accretion, and disk instability. So in the standard model, basically the idea is that a giant planet is forming in a way similarly to terrestrial planets. So you start with the coagulation of planetesimals and you form a core. It could be by accretion of planetesimals or pebbles or both. And then when you form a core which is massive enough, you have a gravitational pull that is strong enough to accrete hydrogen and helium gas from the disk. And then if the growth of the core is fast enough and efficient enough, you will end up having a gas giant planet. In the disk instability model, the idea is different. It is linked to a gravitational collapse, and the idea is that at early times, when disks are massive enough, you can have a local instability in the disk, and therefore you have a region that collapses and become gravitationally bound to evolve to become a gas giant planet. And the reason that people thought that determining the core mass of Jupiter is very important is because it could constrain the formation process. Since if Jupiter has a core, it would suggest that Jupiter cooled by core accretion, and if the core mass is estimated to be 0, it's formed by disk instability. Now we know that these views are oversimplified, because in fact, even in the core accretion model, one can have giant planets with very small cores, and also cores can actually get eroded during the long-term evolution. And in the disk instability model, cores can be formed by settling of heavy elements toward the center when the clump is cold enough. So life is more complex than this, but it just gives you the motivation why it is important to put limits on this property, because it can really enhance our understanding on how giant planets form. Okay, so a little bit about the core accretion model. The reason that this is known as the standard model for planet formation in general, it is because it's very intuitive and it can lead to the formation of different planetary types. So what do I show you here? Here you see the mass of the planet. Typically it's given in Earth masses as a function of time. On purpose, I don't have numbers because it really depends on the model one assumes. But the early stage, which we tend to call phase 1, basically we have a buildup of a core. And the core is represented by heavy elements. So that's the heavy element mass by this red line. Then we have the hydrogen helium mass, and then we have the light blue line, which is the total mass. So the blue line is the blue plus this line. And you can see that the early stages is dominated by building up a core. And if you stop the formation of the planet in this phase, in phase 1, you end up with a terrestrial planet. So this is when you have the formation of a heavy element core via planetesimal or pebble accretion. So this is how we think terrestrial planets are formed. Then there is a second phase, and this is when steadily you also accrete hydrogen and helium from the disk. So the heavy element mass is increasing only very, very slowly, but there is a buildup of an atmosphere, and this is what we call phase 2, which is typically the longest phase in the formation of a gas giant. And during this phase, if I stop the planetary formation during phase 2, I can explain the formation of planets like Neptune or mini Neptunes. And again, this phase is characterized by having the core massive enough to accrete and retain hydrogen and helium gas. And then there is the third phase that leads to the formation of a gas giant planet. And this is basically when the hydrogen helium mass becomes comparable to the heavy element mass, and we have the beginning of runaway gas accretion, and we end up with a giant planet. So this is why, as I said, this model is quite appealing, because it can naturally lead to the diversity of planetary objects that we now observe in our galaxy. And the exact details of how long it takes and what are the ratios between these two depend on the model assumption. So this is something we are working on. Okay, but these are the 3 phases for giant planet formation. But where do the heavy elements go? So historically, in the first models of giant planet formation, it was assumed that all the heavy elements that are accreted by the planets find their way to the center. And this is why basically the heavy element mass was the same as the core mass. But that was done just to simplify the numerical calculation. And if you look at more advanced studies and you actually look at the physical problem, you see that once the planet has already a little bit of an atmosphere, the heavy elements actually evaporate in the atmosphere and do not reach all the way to the center. And this occurs already when the core reaches masses of a few Earth masses. And after that, most of the accreted heavy elements actually remain in the envelope. So this assumption of the total heavy element mass is the same as the core mass is clearly a wrong assumption. And then you can ask, then how do we define giant planet cores? So this is not easy, and I give you some ideas here. Is it by the physical state of the material? For example, if it's a solid core or it's high density. Is it the requirement for having a density discontinuity? So if I have a density jump, then I say, well, this is the location of the core. Is it the stability against convection? So if I have a stable inner region, is that the way to define the core? Or is it the fraction of the high Z material that should be sufficiently large? I don't have good answers because all of these possibilities are valid. It just shows that there is no clear way to define it, and people may think about giant planet cores in a different way. But for me, and today for this talk, I would assume that a good way to define giant planet cores are by the deep interior where the heavy element mass fraction is sufficiently large. So as I told you before, new models of giant planet formation show that actually you can build up composition gradients in the deep interior. And this is because once you have this hydrogen helium atmosphere, the heavy elements can stay in the atmosphere and you don't have this distinct core plus envelope model. And just when you end up forming the planet, you can have something that looks like that. Here you have the heavy element mass fraction. So one is pure Z, right? As a function of normalized mass. This is when we ended up at Jupiter's mass. And you can see that you have this innermost region where you really have composition gradients. And then of course the heavy element mass fraction becomes low because it is a hydrogen and helium dominated object. And if you look at the giant planet in this perspective, you recognize that, first of all, the core is not distinct from the envelope, right? Because it's kind of a continuous gradient. The core region can also include hydrogen and helium. And again, if you have this composition gradient in the deep interiors of giant planets, it also implies that giant planets are not fully mixed, are not fully adiabatic, and are not fully convective. And that's really a change of thinking regarding gas giant planets. So again, the cores of giant planets. So I told you that recent formation models show that giant planets are expected to develop these composition gradients. And in fact, the nature of this composition gradient depends on the local conditions where the planet is formed, in particular on the ratio between the heavy element accretion rate and the gas accretion rate. So here we showed Z as a function of mass for a formation model of Jupiter, and the only thing we change is the solid surface density at the location of Jupiter. So here, this is twice minimum mass solar nebula, and here it's 3 times. And you can see that the gradient is somewhat different. So of course, these two models would have a slightly different total heavy element mass, but you can see that the nature of the gradient is also very different. And again, what is the metallicity in the outer part of the planet? That actually depends how many heavy elements can be accreted during the runaway gas accretion phase. But if you zoom into this region for planetary masses between 0 and 20 Earth masses, you can see that just by changing the local conditions, so the solid surface density, or if you wish, the metallicity of the disk where Jupiter formed, you can see that I will end up having planets with a different internal structure and different total compositions. And this is very nice because it can explain the diversity of exoplanet in this mass range. So we know that there are many exoplanets that have masses between, a few Earth masses to 20 Earth masses, and they all have quite different hydrogen and helium mass fractions. And this can easily be explained by that model, because if they formed in slightly different conditions, they would just end up having different compositions. And as I said, the total composition of the gas giant planet would depend on how many heavy elements are accreted during runaway gas accretion or later after the planet had formed already. But what I told you was about the formation of the planet. And when we observe planets today, when we observe Jupiter today, it had time to evolve. Jupiter age is a few times 10 to the 9 years. And the question is, what happened to the deep interior during the long-term evolution? And in this study, we assumed that Jupiter formed with composition gradients that are quite extended. And we just wanted to see what happens to this gradient. And we found that the outer part of the composition gradient, where the mean molecular weight gradient is not very steep, convection can mix the outer part of the gradient. But the inner part of the planet remains with this composition gradient. So the conclusions are that the deep interior of Jupiter or giant planets are not fully mixed and not fully convective, and also that this primordial composition gradient, if it mixes due to convective mixing, can lead to the enrichment of the metallicity in the atmosphere. It's also important to note that most of the mixing occurs actually at early times when the cooling of the planet is most substantial and convective velocities are the highest. Okay, so now I'm moving to planetary interiors. So again, just to compare these two perspectives of the solar system planets and the exoplanets, again, in the solar system, we have only 8 planets, right? But we have very accurate measurements. And for exoplanets, we have many with large uncertainties, but again, we have statistics. So when it comes to exoplanets, the way we characterize them, we basically try to put them on a mass radius diagram. So for this, we need to have both the mass and the radius measured. And then we can try to estimate what they are made of. So this is a bit old, but it emphasizes the point I want to make. Here you see the radius in Earth radii as a function of mass in log scale. And what we see here, we see the solar system planets. Here you see curves for pure iron, rock, water, and these are some exoplanets that have been observed. And then if we have, as I said, the mass and the radius, and I put the planet here, then I can say, hey, its composition is consistent with that of rock. Of course, this is a non-unique problem, so the actual composition of this planet can be different, but at least I can locate it and say what it could, what the composition could be. But the first exoplanets that have been discovered were actually giant planets. And that was also a surprise, not just because of their location, but also because when you put the mass radius curve of pure hydrogen and helium, which is shown here, this is for 10 astronomical units, and this is for 0.2 astronomical units, all the planets, or many of the planets, were found to be above this curve. And of course, we don't expect planets to be composed of things that are lighter than hydrogen and helium in protosolar composition. And actually, they were even larger than what one would expect from pure hydrogen. So this is how it came to open up the question of inflated giant planets or these hot Jupiters to understand what is the mechanism that leads to this inflation of the radius. And this is actually something that is still being investigated by many groups. And when it comes to exoplanet characterization, what we can definitely see is that the planets, they sit on very different regions of this diagram. So we know that they are very diverse. And what we try to understand is how the composition of the planets depend on the stellar metallicity, the radial distance, the planetary mass, the age of the system, and so on. So this is really what we are trying to do. And of course, we can help ourselves by thinking whether there are compositions that are rather impossible or more likely. So this is what we are doing. But from this slide, you can already recognize the importance of understanding the equation of states of materials, because by having this curve of a hydrogen-helium mass diagram, I can already say whether the planets, this is for giant planets, right, is expected to have also whether it's going to be enriched in heavy elements or there is something else going on. So we really need to have a good understanding of the materials at planetary conditions. So now I'm going to tell you a little bit about the phase diagram of hydrogen. When it comes to modeling giant planets' interior, it is really not easy to model them because of the very high pressures and temperatures in their deep interior, and the equation of state is rather difficult to calculate, and this is because we have molecules and atoms and ions, they all coexist and interact. Okay, so what do we see here? As I said, this is the phase diagram of hydrogen. You see the temperature here in Kelvin in log scale versus pressure in megabars. And here you have curves for Jupiter and Saturn. For Jupiter, there are two curves to show diversity of the models. But what are the conclusions that can be made from here? So first of all, you can see that both Jupiter and Saturn sit above the solid phase. And the conclusion you can make from that is that giant planets are fluid. So you should think about them as not as a gaseous planets, but as fluid planets. And the other thing is that in this region, basically, we have, instead of having molecular hydrogen, we have metallic hydrogen, which is here identified as atomic fluid. So once in this region of Jupiter and Saturn, basically we have metallic hydrogen. So hydrogen becomes dense enough and it becomes electrically conducting. So here you can already see that there is a strong connection between high pressure physics and planetary interiors, because we can already conclude some interesting things just by understanding the hydrogen phase diagram. And for example, the fact that hydrogen becomes metallic at high pressures and temperatures already helps us to understand the origin of the magnetic fields in Jupiter and Saturn, for example. There is an additional complexity when one thinks about the phase diagram, and this is linked to helium demixing. So it was predicted by Dave Stevenson already in the early 80s that helium will demix from hydrogen, and therefore there would be a discontinuity in the helium abundance within the planet. So basically there would be a helium poor and a helium rich region. So that was in the early 80s. And it was confirmed by relatively recent DFT calculations of the equation of state. So this is the phase diagram of hydrogen and helium. And you can see that this is the region of demixing. And you can see that Saturn suffers more demixing in comparison to Jupiter. So that leads to another complexity. So again, I remind you, so we have the region of molecular hydrogen, we have the region of metallic hydrogen, and then we have the issue of helium demixing. How do we model giant planets? For the solar system, again, because we have more data, we have the mass, the radius, the one-bar temperature, and we also have the measured gravitational harmonics. And what we do is we use the equation of states, we assume the composition of the planet. This is something that has to be assumed. Then we solve the structure equations, so mass conservation, hydrostatic equilibrium, the thermodynamic equation. And then we calculate the gravitational harmonics for this structure model. And from that, for a gas giant planet, we can get the mass and distribution of the hydrogen, helium, and the heavy elements. And then, of course, one can compare the model gravitational harmonics to the measured ones, and then you can iterate until basically you find a solution that satisfies the measured data. this is a bit technical, but just to show you here. So basically, this is the gravitational, the total potential of a giant planet. So this is the gravitational potential plus the centrifugal potential. And the idea is that you can expand the gravitational potentials with Legendre polynomials, and then you have these J's. And these J's can be measured by a spacecraft. And once you have these gravitational moments, you can connect them to the density profile. And here is just a plot of the contribution functions. And so here, this is for a Jupiter-like planet. So you have the normalized radius, and you can see, so these are the different J's, and then you use them to get information about the density profile. The higher you go in terms of the J's, actually it probes more the outer regions, but indirectly you can use this information to better constrain what is happening in the deep interior. But in any case, the constraints that we have for measurements or from the space missions are on the density profile of the planets and not the composition. The composition is inferred from the models, as well as the presence of a core. So when it comes to modeling the interior of Jupiter, it is clear that as we have better observations and more accurate measurements, we have less freedom in modeling the interior. And this is how we can further constrain the structure of Jupiter. So as I said, it is not easy because we have the high pressures and temperatures which do not exist on the Earth. And this is why we have to rely typically on theoretical calculations and calibrate them with experiments that are done on our planet. And I remind you that I said that for the hydrogen equation of state, we have the transition to metallic hydrogen. We have the issue of demixing, which we often call helium rain. And then, of course, we also have the heavy elements. And of course, as I said, everything is interacting and it's complex by itself. And nevertheless, despite this complexity, we make many simplifying assumptions. Typically, structure models are 1 or 2 dimensional. Often it is assumed that the planet rotates uniformly, and then we just add some dynamical corrections. And of course, our models do not have magnetic fields. So before the Juno mission, this was a standard structure of Jupiter. So it had 3 layers. So what are the layers? So we have an inner heavy element core. Then we have a region of the metallic hydrogen, which is also helium rich. Here we have the transition where we have the helium rain, and then we have the molecular hydrogen that is also helium poor. So that was kind of the idea, because that was the minimum number of layers one had to use to model Jupiter based on the knowledge we had, again, from the equation of state of hydrogen and helium, and also based on our understanding of planet formation. So again, it's a simplified view, and for the heavy elements, so somewhere in the core, and typically models assume that the heavy elements within the interiors are homogeneously distributed. Yeah, so basically above the core, the heavy element mass fraction would be the same in these 2 regions of the envelope. But that was before the Juno mission. And in 2011, the Juno mission was launched, and it arrived to Jupiter in 2016 on July 4th. This mission has 43 days polar orbits to allow a good measurement of the gravity field. It is still ongoing, and it might be extended even further. It is very rich in terms of scientific instruments, and I could give an entire talk just about Juno measurements and Juno data. But a key question that we try to address with this mission is to better understand the formation of Jupiter. So, as I said, how did Jupiter form? When did it form? Where did it form? How long did it take it to form? So the main science objectives are written here. It's really to understand giant planet formation and evolution by better understanding the origin of Jupiter, its internal structure, the atmospheric composition and dynamics, and magnetospheres. So it's really a comprehensive mission, and it touches these different aspects. Here you can see some key questions of the mission, as I said. So how did Jupiter form? What is the internal structure? Does it have a core? Does it rotate as a solid body? How is the magnetic field generated? How deep are the atmospheric winds that are observed? What are the physical processes that power the aurora? and how do the poles look like? And this is something we could answer only recently. So as I said, there are many key scientific questions, but I'm really going to focus on these two. So how did Jupiter form and what its internal structure? And this is done by, as I just told you, is by having accurate gravity data. So if we have the gravitational harmonics of the planet, we can further constrain the internal structure. And here I show you some data from 2018 paper led by Luciano Reyes. And you don't need to be experts in the field, but the point is to look at the uncertainty. And if you have a little bit of intuition for this problem, you can see that the uncertainty is tiny. It's really tiny. So in terms of gravity data, it's wow, it's really amazing. And what I show in this plot is the J6 and J4 of Jupiter from different solutions before Juno and some solutions from structure models. And this is the first Juno measurement. So actually it was even less accurate than what is shown here. And you can see that it's tiny. So suddenly when you have this really super accurate measurement of the gravity field, suddenly you need to have the models fitting that. And as you can see from this example, actually there was no model that could satisfy the gravity data. And that led to the establishment of new structure models of Jupiter that can fit Juno data. So this is still work in progress, but two key models that were published are by Valetal in 2017, where it was suggested that Jupiter has a fuzzy core, and that was confirmed later in 2019 by an independent group, Debras and Chabrier, suggesting that basically Jupiter has composition gradients in its deep interior that can extend up to 70% of the planetary radius. So here you have these composition gradients, which I told you about when I discussed the formation of Jupiter. And this is really great because it's the first time when we have a link between the planetary internal structure and its formation mechanism. So these models of Jupiter that really are based on data suggest that Jupiter is non-homogeneous, not fully convective, and has a fuzzy core. And as I said, this is also what recent formation models suggest. So this is a very nice way to link these two aspects. However, although we do have a much better understanding of planet formation, and as I did show you before, formation models suggest that you build up composition gradients. The fuzzy core that is found by structure models is much more extended than what is found by formation models. So in the structure models, this fuzzy core can involve something like 100 Earth masses, so 30% of Jupiter's total mass. So can we really explain it from planet formation theory? In a recent study, we basically addressed that. We try to be very generous in the formation process of Jupiter and build up very extended composition gradients. Please have a look at the paper if you're interested. Basically, we allowed primordial composition gradients. We allowed significant heavy element accretion during runaway, as well as no accretion at all. We had hot start and cold start. So we changed the primordial entropy. And we try to see, do we have a model that would end up looking like Jupiter today? So here you can see these are 4 different models. And here you have basically the normalized mass as a function of time. And the blue region represents the region that is fully convective, while this light orange shows the dilute core region. And you can see that even when we start with very extended, super extended dilute core regions, as time progresses due to convective mixing, the gradient is being eroded. And at the age of Jupiter, it is much smaller than what is predicted by the structure models. So these are indicated here. So you can see it's much below the dashed curves in all the cases. So although we managed to have primordial extended composition gradients, we find that they are being eroded, leaving the planet with relatively compact cores. So this is something we're still working on, and you can see here the same conclusion, just looking at it in a different way. So this is the heavy element mass fraction as a function of normalized mass. These are from the structure models, from 3 different structure models. And here you can see the 4 formation models we had, and you can see the dashed is the primordial composition gradient, and the solid one is at Jupiter today. And you can see that there is no way to keep the composition gradient so extended. So the conclusion is that forming a fuzzy core in Jupiter is actually very challenging in the standard picture of giant planet formation. And again, to simplify, I show it to you here. Here I have the heavy element mass fraction as a function of normalized radius. And the idea is that formation models can have this fuzzy core, but typically it's up to, bit more than 20% of the radius, while the structure models might suggest that it can go up to 70%. So although on a quantitative point of view, there is some agreement, it is not exact. So now we go to the next level and think, hey, how can we explain that? How can we improve our formation models? So one potential solution is to have an extended phase 2. So if you remember, the phase 2 in giant planet formation is the phase when you accrete gas in a steady way and a little bit of heavy elements. But in fact, if you manage to accrete more heavy elements during this phase, it can delay runaway gas accretion. And this is because by accreting heavy elements, one provides more energy to the planet, and the planet has to cool down, and therefore it delays the moment where it goes to runaway gas accretion. And this can be by accretion of relatively high accretion rates of planetesimals. So this is just to show you. So here is the heavy element mass fraction as a function of planetary mass going up to Jupiter mass. And the idea is that during phase 1, if you remember, it's dominated by heavy, so it's around 1. But then we have this phase 2. So we have accretion of both hydrogen and helium and heavy elements. And then runaway gas accretion is delayed and happens only at about 100 Earth masses. So this could lead to something that is more consistent with the structure models that are made that fit Juno data. Okay, or if you want to think about it, you can think about it in this way. Again, it's the heavy element mass fraction versus mass. So again, depending on the exact model assumptions, but the idea is that you have these composition gradients, but instead of having it going to the first, let's say 20 Earth masses of the planet, it can be extended up to nearly 100 Earth masses, which is much more consistent with the structure models. And the interesting thing about this idea is that it can help us to explain the formation of Uranus and Neptune-like planets, or mini Neptunes, as well as to understand why the transition to gas giant planets occurs at around 100 Earth masses. So this is something that we are working on now. And I think it opens up many interesting research directions. There is another potential solution, and this is that, like many other planets in the solar system, Jupiter suffered from a giant impact. And the idea is the following, that before the impact, we had this, let's say, fuzzy core, but it was relatively compact, and there was an impactor that has to be quite massive, 10 Earth masses, for example, and the impact is head-on. And you can see that after the impact, the internal part of the planet is much more extended, the density is lower in comparison to the before the impact. So this could lead to a formation of a fuzzy core. So here I show you a movie that shows this impact. So you can see we had the proto-Jupiter with a relatively compact and dense core, and due to this impactor, the core got extended, becoming more fuzzy, so lower density. So this is also a possibility. It's not the first planet in the solar system that we need to have a giant impact to explain its properties. But I have to be fair and say that the outcome depends on the assumed impact conditions and also the primordial conditions of Jupiter, and you need very specific conditions. So you have to be lucky. It doesn't mean that it didn't happen, but okay, it's up to you to decide. Okay, so conclusions and future research. Giant planets are complex, really. 20 years ago, it was thought that they are just, spheres of core plus envelope, boring, fully convective objects. This is absolutely not the case. But in order to characterize those planets better, we need a new generation of planetary models, both in terms of formation, evolution, and structure. Formation models suggest non-homogeneous internal structure, not fully convective planets with composition gradients and fuzzy cores. Clearly, the composition and internal structure of giant planets are determined by their formation and evolution history. And as I said, we must link these three aspects. And Juno data confirm this view of giant planets, but more work is needed. So in terms of perspective, what should we see in the next years and decades? Combined planetary science and astrophysics. This is really critical because, as I said, these are two complementary groups, and we should take advantage of the very accurate measurements we have in the solar system, together with the large statistics that we have from exoplanets. And like that, we can really push planetary characterization to the next level and also try to identify the uniqueness of our own planetary system. We also want to connect to high pressure physics. And this is because, as I told you, knowledge of the equation of states of planetary materials is critical for planetary models. And also it can guide us in terms of model assumptions. So we know under what conditions some materials are more likely to be differentiated or mixed. So we really want to use the information of the behavior of planetary materials in conditions that we have in planets, so we can further constrain our planetary models. Of course, we want to combine theory and observations. We have the theorists and we have the observers. We can provide theories, strategies, simulations, and predictions. And of course, the observations give us the data and the measurements we need. But again, we should combine the two. So having the data can help us to make progress in theory and test our predictions, but it can also help us to guide future observations. And as I said, we definitely need to combine these three sometimes separated aspects of planetary formation, evolution, and internal structure, since there is a clear interplay between the three. And in order to better understand one aspect, we definitely need to better understand the others. So I will leave you with a nice movie from Juno. So this is from Juno Cam. This is a camera that was put on the spacecraft actually for public outreach. So we don't really do science there. This is, by the way, false enhanced color. So this is not exactly how Jupiter looks like. It looks much more pastel, but you can clearly see the beautiful dynamics that occur on this planet. So really beautiful storms. And I think this mission really gave us a new way to look at Jupiter, not just because of this JunoCam data that you can see all this convection and storms, but also because of the gravity data, as I said, that basically tell us that giant planets are much more complex than we think. And to me, it's a new way to think about gas giant planets. Thank you very much.
Thank you, Ravit, for this